Hi everyone, in this video I'm going to talk about Riemann integration and measure spaces. So measure spaces are sort of a jumping off point where we start to get into Lebesgue integration a bit, but so this will be both important to Riemann integration and to Lebesgue integration at this point. So I'm just going to have a few definitions here that you guys might not have seen before because they only really start to arise in this context of Lebesgue integration. So the first definition is what's called a sigma algebra. And that's always with respect to a universal set X. So X is our universe for the time being. Nothing really exists outside of it. And then sigma is a set of subsets of X. So if you like, it's a subset of the power set of X. We say that set of sets, sigma, is a sigma algebra whenever it satisfies the following three properties. So the first one is that the empty set has to be a member. It's pretty easy to satisfy. That it is closed under complement. That means whenever A is in the set sigma, so is A complement. Finally, that it is closed under countable union. That says that if you give me a collection, a countable collection, AN, all of which are in sigma, then its union is in sigma. So notice this keyword countable here. So if you remember from topology, open sets, an arbitrary union of open sets is open. But in this context, we only say it has to be countable. We do not allow arbitrary unions. So as a few examples, these are the two sort of trivial sigma algebras. The first one is just the empty set and the whole space. Why is this a sigma algebra? Well, it clearly satisfies A. We explicitly put the empty set in there. And it certainly satisfies B, because if I take the complement of the empty set, I get X. Well, that's in there. Similarly, if I take X and I take its complement, well, that's the empty set. That's also in there. And then finally, if I take a countable union of these two things, well, a countable union of a mixture of empty sets and the whole space is either the whole space or empty sets. So nothing, you can think of C as being sort of a generation step. Once I start with sort of a basis, do I generate new sets? And if I do, what do those sets look like? In this context, this doesn't really generate anything new. And similarly, if you take the power set, clearly the empty set's in it, clearly it's closed under complement. And if I take a subset of X and I take countable union of those, it's clearly still a subset of X. If you want, you can look online for more interesting examples, but we'll eventually get there, and I don't want to belabor the point too much for now. And so now this is where we're going to get into the definition of a measure space, which is ultimately where we want to build. So a measure space is, you always have a set X and a sigma algebra sigma. So it doesn't make sense to talk about a measure if you don't have a sigma algebra, because a measure is a function mu whose domain is a sigma algebra that maps to the extended real line. So if you haven't seen this before, this is closed. This is not a typo. We do allow it to say, okay, well, that set has infinite measure. Just a convention. Satisfies just two properties. The first, let's undo that. The first property for mu to be a measure is that the empty set has measure 0. Okay, simple enough. Measures are supposed to measure length of things. So if our set is the real line, an example of a measure is one that just says, okay, well, I'm going to take an interval and I'm going to assign, if the interval is a to b, well, its measure is b minus a. And then from there you can construct what more complicated sets measures look like. But the empty set, no matter what your rule is, has to be 0, which makes sense because the length of nothing should be 0. And similarly, if I take sets, a collection of sets, countable, whose intersection is empty whenever their indices are not equal, then the measure of the union is equal to the sum of the individual measures. And to motivate that, let's look at just a union of two things. So this also this subsumes the countable case because I take the first two as A1 and A2, and then I take the rest of them to be empty sets. So if there's no overlap between this length and this length, then each of them is adding their own length to the set. So the rule for their union should be that you just add them up because there's no overlap. That's what this is saying. There's no overlap between the sets. And then finally, a measure space is simply the 3 tuple given by the space, the sigma algebra, and the measure mu. So measure space is always equipped with those 3. So sometimes you just see people just say, let X be a measure space. It's kind of like when you say, let X be a topological space, and then they don't explicitly tell you. But there's always those 3 objects whenever you say it. So there's just a few properties I'd like to go over for measures. So the first one is countable subadditivity. And that is, if I take an and sigma, not necessarily disjoint now, then the sum, mu of the union, that equality can always be replaced by a less than or equal to. Because notice that I got rid of the assumption that they had this disjoint intersection. I don't know what to call this one, but if... Oh, sorry. Yes. Oh, gosh. Got the huge eraser. If the measure of the whole space is finite, because remember, we can assign infinity to the measure, and B is contained in A, then the measure of A intersect B complement, or A minus B, or A minus B, depending on how you like to denote things. This is equal to mu of A minus mu of B. So intuitively, that makes sense. If this is A, and this is B, then the whole measure should be that green area minus the part that we just cut out, right? Because we're taking the complement. So I'll switch back to orange. I just want to switch back to these, that way you guys know. So then the other one is continuity from above. So this says that if En plus 1 is contained in En, then the intersection then this sequence decreases to the measure of E, where E is the intersection of all these sets. And then similarly, continuity from below says that if En is contained in En plus 1, and that the measure of E is less than infinity, that mu of En increases to mu of E, where E here now is the union of the ENs. So we have to have less than infinity because let's say, for example, that my En was 0 to n, and my length here is, so let's say that our rule is that it's just the length at the interval. Oh, wait. This is not a good example. Regardless, weird things can happen at infinity, so you have to assume that it's less than infinity for that to make sense. So just keep this in mind. So I'll just prove for now these two properties here. I think these are sufficient to get the ideas, and then I'll leave 3 and 4 as an exercise for you guys. I'll start with number 2 because I think it's the easiest one to prove. So we have mu of x, so I'm going to do 2. Mu of x is less than infinity, and b is contained in A. Okay, so this is, and pause the video here if you're not 100% convinced of this, but this is B union A complement. That's De Morgan. So these sorts of set manipulations are important. So if you didn't follow this, pause it and really think about it. Review your De Morgan's law here, because these sort of set manipulations are super important in measure theory and Lebesgue integration. So now, as a little aside, I'm just going to show you guys a property really quick. That mu of, I don't know, let's call it E again. E complement is equal to the measure of the whole space minus mu of E. And again, we're assuming that. And the reason is because mu of x is mu of E union E complement, which is mu of E, let's go down here, which is mu of E plus mu of E complement, and that is from property B of what it means to be a measure, and so that tells us that mu of E complement just subtracts both sides. And notice that if mu of x was infinite, not E complement, then this algebra just doesn't make sense per se. And again, weird things can happen at infinity, so you need that less than infinity assumption. So now I'm going to apply this. That tells me that mu of B union B, A complement is mu of x minus mu of B union A complement. Now, since B is contained in A, again, this is a fundamental set theory here, not too hard to prove. But if you're a bit rusty on these sorts of manipulations, if B is contained in A complement is contained in B complement. And so B intersect A complement is empty. Again, just think a bit here. There's just a little bit of logic there to work through. So pause it here if you need to. And so we're going to use, this is property B again of the definition of a measure. Okay, and then this is mu of x minus mu of A complement minus mu of B. And this term right here is just mu of A. And why is that? We just proved that above. So this is applying it, the green part, with E equal to A complement. Implies E complement is A. Okay, so that's a nice thing to keep in your mind and make sense intuitively because you're cutting out the hole. I'll switch. I think I reversed colors on the other side. So, but now we're going to prove property 1, countable subadditivity. Okay, so I'm just going to show it for A1 union A2. There's probably a way to do this directly, but I'm just going to do it by induction. So is this less than or equal to question mark mu of A1 plus mu of A2. So let's do whole space X here. Let's do A. So this is A1. We'll do A2 in orange. And let's say this is purple here. So in purple here, I'm going to draw the intersection. I'm going to cut this out. So this is A1 intersect A2. So I don't want to get it too confusing. So the point is, this, what is the size of this set, the measure or this sum? Well, that is coloring this whole thing in, adding up everything, and then adding up all of A2 here. And what do you notice when I color this in? Well, I color this intersection in twice, which means that this sum right here should be greater than or equal to the sum of the union, because the union is this set here. It only colors over A1 intersection A2 once. So we're going to formalize that, again, through some manipulation. So I really just want you guys to get a sense of these sorts of manipulations that are often used in these types of proofs. So mu of A1 is mu of A1 intersect A2 complement union A1 intersect A2. So all I'm saying there is it's this chunk here, A1 minus A2 complement, plus union this set here, viewed separately. Those are disjoint sets. So I can add them up. That is, again, property B of a measure. Mu of A, I'll do this in orange, since I drew it in orange up there. Mu of A2, similarly, just flip the roles. This is A2 intersect A1 complement, plus, that role doesn't make a difference. So that tells me that mu of A1 plus mu of A2 is mu of A1 intersect A2 complement plus mu of A2 intersect A1 complement plus 2 times mu of A1 intersect A2. Okay, so we have that stashed away. I'm just going to do a different color here entirely. Let's go to red. Now let's compute. So that's stored away. This is mu of A1 intersect A2 complement union A2 intersect A1 complement, or you're in the common region A1 intersect A2. So again, all I'm doing pictorially here is first I add this up, then I add this up, then I add the intersection up, and that gives me precisely the set, but they're disjoint pieces. So then again, I apply property B. that says, okay, these are disjoint subsets. So I add them up. Now, this is less than or equal to this sum. Right? If I multiply that by 2, it maps into positive or non-negative numbers. But then this is exactly equal to this. And notice that when they're disjoint, this is the empty set and it's just equal to 0 so that the equality is exact. So it's also consistent. And then, so then by induction, and you can fill in these details if you like, by induction we have countable subadditivity. You just have to do a limit argument, basically. So hopefully that gives you guys some intuition. And then on the next video, we'll really get into what Lebesgue measure is and how we're going to use it for the Lebesgue integral, as well as how it is connected to the Riemann integral. So we're still in Riemann integration, but we're pretty close to getting to the point where I'm going to show you guys Lebesgue integration, because there's a little bit of overlap at the end of your Riemann integration introduction stuff to motivate Lebesgue integration. Thank you guys for listening.